from last time, and then I'm going to pass to arbitrary fields. So the loose end is really the key theorem of the subject, which I really need to mention. This is the following. So if X is smooth, projective, minimal, and rational, then X is one of the following: P2, P1 cross P1, or Fn. This is usually called the Hertzebruch surface. And so this is the projective bundle and to avoid double counting, I'm going to assume that n is not equal to 0. And to avoid false statements, I'm going to assume that n is not equal to 1. So we have n greater than or equal to 2. So these are all the minimal surfaces over an algebraically closed field. Now, I have to confess, as a student, I sort of took this as gospel. And I never really thought about why it's true. And to prove why it's true would take me the rest of the week. So you're not going to learn why it's true today, except in sort of a schematic sense, which is probably good enough to get most of you started. So what's the key ingredient here? So if you have a rational surface, it follows that the canonical class is not an F. In other words, there exists a curve C This is good because the games that we were playing in the last lecture, where we would identify extreme arrays, contract them, and get simpler surfaces, we can't play that game if we don't have some negativity. And so this is what allows us to. So this allows us to play. So play extreme games. Extreme array game. Now, the key ingredient, I'm going to assume this for the time being. I'll say a little bit more about how to think about it. But so assuming this, let's let R be an extreme array. So this is extremal in the sense of convex geometry with KXR negative. So we have on the other hand, our minimality assumption implies that R squared has to be greater than or equal to 0 because it's not a -1 curve. So then we use our classification result of the extremal contractions. So we get the contraction associated with R, which takes X to some Y, and there are two possibilities. So the first possibility is that this is a P1 bundle, and Y is a curve, or this is just P2, and Y is a point. So if we have a P1 bundle, then in the first case, so we get the fn's for n equals 0, 2, 3, etc. And in the second case, we get P2. So this is the outline. It uses the analysis of the extremal contractions that we sketched out last time. So let me come back to the key ingredient now. So how should we think about the key ingredient? So I really mean this sort of rhetorically. So the real key, necessary concept behind this is abundance. And so let me give you a sample statement of what we mean by abundance. I think abundance, the term is kind of a joke. I don't know the history, I'm too young. But ample means you have a lot of sections. Abundant is a little bit weaker than ample. It means you have sections, they're prevalent, but abundant sections are fewer than ample sections. So you should see this as, in some sense, a weakening of ampleness. And so the statement is that if X is a smooth projective surface with kx nef, then
Excuse me.
Okay.
It's ready. Sorry for the interruption.
No, that's fine. Okay. By definition, x is minimal. If any birational morphism over K from X to Y, where Y is smooth, if any such birational morphism is an isomorphism. The main result is X is minimal. Remember, if X is over an algebraically closed field, it's minimal if and only if it has no -1 curves. Here, we need to account for the action of the Galois group. We need to say that X admits no Galois invariant collection E1 through ER of pairwise disjoint -1 curves. And I guess I should, one bit of notation while I'm at it. I'm going to tend to use gamma for the Galois group. So the picture is, if you have a collection of -1 curves that are permuted and conjugated by the Galois action, I can try to just blow them all down together. So let me say something about why this is true. I guess I should say it like that, yes. So I want to think of these as -1 curves on X bar. So let's suppose that X is not minimal. So I have my contraction. Now we know that X bar admits a -1 curve. Contracted by phi. And so let's let E1 through ER be the corresponding Galois orbit. So these are all the conjugate -1 curves. You should think that the -1 curves are parameterized by some variety, which is defined over K. And so the Galois action permutes the points of that variety. So, I mean, you can think of another way, more concretely, is you can think of these as being defined by some equations. And I just let the Galois group act on the equations. It takes one -1 curve to another. Now, let's look at, for two of these, let's look at the why is the orbit finite? Well, because, I mean, the -1 curves are defined over some finite extension. If they weren't, if they were defined over some transcendental extension, they'd be deforming in families. The rigidity of the -1 curves, there's only going to be a finite number of them, means that they're defined over some finite extension. Yes?
Why couldn't it become an isomorphism after going to algebraic closure?
Being an isomorphism is stable under base change. If you have a morphism, if it becomes an isomorphism after base change, and it was an isomorphism in the first place. So that's a fact that I don't think I want to try to prove here.
You don't even need that they don't prove because they are defined over the algebraic closure of K. So they are defined over a finite extension.
They are, yes, they are defined over. There's lots of ways of seeing that, although I don't want to. Basic descent facts are not one of the courses, unfortunately. So I can't say much more about that. So we have this orbit. Oh, I should say, and these are all contracted. So this is a quick and dirty way to see that there are only a finite number of them, right? Because there's only a finite number of curves that are contracted by the morphism. So the finiteness in this case is extremely easy. So if I have two distinct elements here, I can look at the intersections, and I see that this is negative definite. Right? So whenever you have a blow-up, the exceptional locus, it has a negative definite intersection form. So I get that -1 squared minus the self-intersection is less than 0, which forces the curves to be destroyed. So let's come back to that was probably, I'll probably never, oh well. So for the other implication, let's see, which one? I'm sorry, I need to, is that what? Oh, I'm sorry. Yes. Sorry, the determinant of a negative definite 2 by 2 matrix is positive, 2 negative eigenvalues. Yes. So this gives me that this is necessarily 0. So on the other hand, let's say that we're given E1 through ER, Galois orbit of distinct destroyed -1 curves. So let's let H be ample on X and defined over K. And note that H intersected with each of the components. These intersections are the same for all I and J. So what I'd like to do is I'd like to consider just like with Ovo theorem, I want to consider this line bundle. And because these coefficients are the same, well, this is certainly element of pick X bar, but it's Galois invariant. So, is there a question? Okay. So, we know that the Picard group of X is the kernel of the map from the Picard group of X bar. Well, thanks to Andrew, I can use the Brouwer group, right? He told you about the Brouwer group. So we know that the Picard group of the variety is the kernel of the map from the invariant part of the Picard group to the Galois group. So let me at least reduce this to a spectral sequence for those of you who are so inclined. So you should think of this as being the map from H0 Galois cohomology to H2 and this is H1 of OX star. And this, of course, here is just K bar star. So this is a Brouwer group. Now, the one thing I want to emphasize about this is that the Brouwer group is a torsion group. So in particular, it follows that n times h is contained in pic of x for some n sufficiently large. And so I just take the contraction the sections of multiples. And this gives me a variety defined over little k on which all of these things are contracted. And the proof that worked in the algebraically closed field also works to show that this is a blow-up. So this is the argument.
This last gamma is a section.
I'm sorry?
This last gamma is not a gamma.
Oh, that's pretty terrible, yeah. Too many gammas running around. There. Okay. So we have this result. What I'd like to turn to now is how do we actually classify these things? So I'm erasing our old classification theorem because I want to replace it with a new one. I want to classify all the minimal rational surfaces. To do this, I need to introduce a new class of surfaces called conic bundles. So these are surfaces that we didn't have to worry about in the algebraically closed case, but they play a very important role in the non-closed theory. So a conic bundle consists of a minimal surface X. So there's a minimal projective rational smooth surface. And the dominant morphism f from x to c, where c is isomorphic to P1 over the algebraic closure. C might not be P1 over the ground field. It might be some more complicated conic, but it's geometrically P1. So that the generic fiber F has a property that F over K bar is isomorphic to P1. So, for example, I could let C This is the empty conic, corresponding to the quaternion algebra. And I could take X as C cross C. So non-closed fields, you have lots of weird stuff going on like this. So this is an example of a conic bundle. And I mean, whatever else we do, we don't want to have to classify conics here. That's Andrew Kresch's domain. So we're not going to try to analyze what all the possible conics are. We're going to assume that someone else knows how to analyze that stuff. And we're just going to express our geometric results in terms of these conics. Okay, let's see. Maybe I won't erase that. So let's give some description of the degenerate fibers. Before I do that, let me make a remark. I should have made this remark before, but now is also a good time to mention it. So if our field is algebraically closed, then the 10-Lang theorem guarantees a section S from C, which in this case is isomorphic to P1, to X. So we always have a section of a conic bundle. So this implies, so since X is minimal, we necessarily have that X is a projectivization of a vector bundle which is necessarily isomorphic to the projectivization of the split bundle by the classification. So,
The rational section.
a priori it's a rational section, but the morphism is proper. So the valuative criterion allows you to extend the rational section to a regular section. So when you're working over a function field of a curve, the valuative criterion allows you to identify rational sections with regular sections, provided the morphism is proper. So this is why we don't care about conic bundles. So in fact, we only care about conic bundles without sections. The second thing I want to emphasize is that every conic bundle has a bisection. This is why they're called conic bundles and not rational curve bundles, in some sense. So if I have a conic bundle, I can always find a bisection. Well, that was a rather poor choice of figure. Let me try again. If I have a conic bundle, I can always produce something that intersects each fiber twice. The reason is that if I look at the relative canonical class, this intersects each fiber, well, minus this, intersects each fiber in degree 2. And you can, by suitably localizing the base, you can always find a bisection. So this may not be effective, but if you shrink enough, it will eventually be effective. Another way of saying it is that you just restrict to the generic point of C, and every rational curve, smooth rational curve over a field, is isomorphic to a conic over that field. Yes, I do mean that. Thank you. So let me classify the singular fibers. The minimality puts very strong constraints on the singularities of the fibers. So let's identify what these are. So this is the singularity classification. So the first part, you should see the singularity classification part of the justification for the terminology. I'll show that all the fibers are actually conics. Given a conic bundle, so any singular fiber consists of two minus 1 curves, meeting at one point. So I have the smooth fibers. The singular fibers really just look like degenerate conics in the plane. The second part of this I'm not going to talk about much, at least not talk about the proof, but it's morally important, so let me state it. So, in fact, we have an embedding. So I have X over C, and then I want to look at the projectivization of the dual to the relative dualizing sheaf. So here, omega f is just O of k of f. I have an embedding from x of x into here over C. This is a P2 bundle. And here, the fibers are realized point by point as plane conics. So this is, I think, the full justification for why conic bundles are conic bundles. I mean, why they're called that. Yeah, well, we knew that, I mean, there are conic bundles that are minimal. I could just take a product of a conic with C, and that's going to be minimal. Yeah, you have to have a singular fiber to be non-minimal. There's no, I'm not saying any singular fiber that might occur will look like this, but there's no guarantee that there are any singular fibers. Okay, so let's see. Watch this out. Is there another question? Okay. So here's a, sorry about that. Hopefully it'll just go away. So let's let F be a singular fiber. The one thing that we know is that if I look at the corresponding F bar and X bar, this is not minimal anymore, just because of what, I don't know the name, but whoever asked that question, that's exactly what I'm doing here. This is not minimal, and so we have a -1 curve in F bar. So let's look at the corresponding Galois orbit. So a lot of stuff can't happen. So let me draw a whole bunch of pictures. Well, the first thing is that they're not disjoint. We know they're not disjoint. Now, here are a whole bunch of impossible cases. I can't have, say, three curves meeting once, right? Because of the genus. Ditto for 4 curves. I can't have 2 curves meeting twice. These are all impossible cases because the fibers have genus 1, a genus 0. So these are not allowed. So what's left? What can we realistically have? So the only possibility is that R is equal to 2 and the two corresponding components meet at one point. Okay? So there might be other garbage, right, that other than those two key components. How do we show that there isn't any other garbage that we don't want? So here's the idea. So let's let E1 to En be all the components. Of F. And let's write the fiber as a sum. So Mj is the multiplicity of Ej in the fiber. Now, the intersection form. Well, I can think of it as living on the direct sum of all the components. Right? You give me two components, I can intersect them. But the one thing that you have to remember is that the fiber moves away, right? The fiber isn't stuck there. I can move the fiber to the right a little bit. I mean the scheme-theoretic fiber. Since it's a fibration, the fiber moves. So we know that F intersected with each of these is equal to 0. So really, I should think of the intersection form as not living here, but living on this quotient. Because, I mean, the fiber itself doesn't really play any role here. And then on this quotient, we get that the intersection form is negative definite. So the only places where it vanishes on F is on the only place it vanishes here is on F. Okay. Well, let's come back here. What is this? 0, right? -1, -1, +1, +1. So we get 0 for this fiber. So it follows that from this analysis is that the fiber is just equal to E1 plus E2. There can't be anything else because anything that goes to 0 under the intersection form, it has to be in the kernel of this quotient. Therefore proportional to the fiber. I guess I proved it's proportional to the fiber, but the constant of proportionality is 1. So coming, let's see. Let me just make precise the description of all conic bundles over the algebraic closure. So a minimal conic bundle X is geometrically the blow-up of some surface Fn at points in distinct fibers. So I have a map from X to Fn. I'm taking some points here and just blowing them up. To get the conic bundle. So here I have my exceptional curves. Yeah, I'm sorry. I don't know how to draw a picture of X. And I'm sorry? Oh, yeah. So here, P. I wish I could work in 3 dimensions here, but the things down here are meant to be the fibration structures. Yeah, so distinct fibers with respect to F from X to C. Okay, well, let me.
Why is X bar non-minimal before we go to the state?
Why is X bar non-minimal?
So you said we have this minus 1 curve in X bar.
Well, if I have a minus, I'm a little if you have a minus 1 curve, it's not minimal over the algebraic closure.
Right, but we didn't know it had a minus 1 curve yet. Right, so we started assuming we have a singular fiber.
Yes.
And then you concluded that in the algebraic closure there was a minus 1 curve.
Because we had the classification of minimal rational surfaces over an algebraically closed field at the beginning of lecture. I'm using that implicitly. So I know that I know what the fibers look like in those. Okay? So I'm using the fact that, yeah. I'm making reference to the result at the beginning. Yes? I can't hear you. I'm sorry. You have to speak louder.
The point, why the minus curve actually live in the fiber at bar? That's because you know at first singular we factored in whatever blow up we were going to take the minimal one. Is that
I use, let's see. So you're saying that I don't know that it's,
yeah, why did it not intersect it?
there might be those too, but I don't want to worry about those. I mean, I'm not saying that,
Why does it contain any minus 1?
you're saying why does it contain any vertical minus 1 curves? So I can take I need to probably keep track a little bit more precisely of the minimal models, but I can do the minimal model in such a way that I preserve the map onto P1. I have a little bit of freedom as to how I take the minimal models of the rational surfaces when I have a map onto P1. And so I should probably take into account that freedom. So you're right. There's a detail there. If I had been more precise about exactly how I do the process, I could prove that I can do it compatibly with the morphism onto P1 so as to preserve the structure of that morphism, provided I have the fibers are rational curves. So if I'm more precise in the description, I can get around that. There's some freedom in minimal models that I can use to control that. So that's an excellent point, and so yeah. So this is something this is one of those things that, yeah. Okay, so.
So what is the condition of the Gauss action on these 12 points?
Well, the thing I know here is that these are conjugated under the Galois action. The Galois action is going to spin these two things around. It's going to flip these. It could also flip things this way, too.
So what about these points which have no
Well, they're definitely not going to be defined over the ground field.
Yes.
I mean, The one thing you can say for sure is that these two things are Galois conjugated, these exceptional curves. So if you look at the action of the Galois group on the configuration of all the exceptional curves, you have to have one to take one from the other. Because if this were fixed under the Galois action, then I could blow it down. I need to state, I'm sorry.
So in the argument there, you're looking at the connected components of those Galois shapes.
I'm sorry, the connected, I was looking at, here I'm analyzing all irreducible components of F.
Okay, but you're saying that the Galois bit will exchange fibers, different fibers.
Oh yeah, certainly you could have, I mean, because these points here may not be defined over the ground field. So,
So when you look at that Galois orbit there, it's going to break up into a union, a disjoint, a union of sort of joint.
I'm sorry, I want to pass to the subgroup of the Galois group that's fixing the fiber. So I pass to a field extension so that the fiber is actually well defined. And then I analyze the Galois action over that extension. So I mean, I need the fiber to be defined over my ground field to do the analysis. So I pass to that base extension and look at that Galois action. And I'm going to have to cut short questions because I have something I need to state before the end of the lecture. And this is the last point where I'm going to be able to do it. So here's the big theorem. So I'm going to write down all of the minimal rational surfaces. Every number theorist should know this list. If you want to study rational points on smooth surfaces, there's no good reason not to study one of the surfaces on this list, right? I mean, if you study other surfaces, you're not going to be sure that you're not doing something someone else has done already. So here's a list. Let's say x is minimal. And x bar is rational. And as smooth projective surface. then either x is P2, x and P3 is a quadric. So that the pick of x is isomorphic to z. So x is del Pezzo with the pick of x generated by the canonical class. Notice that this excludes this, right? Because here the pick of x is not generated by the canonical class. This, however, does include a Brouwer-Severi surface. So these are, I mean, these cases are actually carefully constructed. Or x is a conic bundle with Picard group isomorphic to Z cross Z. Over Q, the Picard group will be generated by the canonical class and the class of a fiber. So these are all of the surfaces that you'll ever want to see. Now, there's some warnings that I should provide to you. So here's there are coincidences between these surfaces. are some coincidences. So you can relate these. If you have there may be some birational connections between these. But every surface is a blow-up of one of these surfaces. So if you want to understand rational points in every rational surface in existence, it suffices to understand rational points on this short list of surfaces. So here's a challenge problem so that you can get a sense of what goes into this theorem. Let's say I have X with the property that X bar is a blow-up of P2 at 9 points. Why can't X be minimal? Just think about it. Take the first case that's not covered by the classification and try to understand how you can shoehorn it into one of these 4 classes. So this in some sense is showing what you're dealing with. You somehow have to produce some collection of -1 curves permuted under the Galois action so that pairwise disjoint so that you can blow them down. Now the thing that makes your life a little bit easier is we have really a lot of -1 curves here. Remember, this was our bad example where we have -1 curves everywhere. If a given -1 curve doesn't work, there's always more to try. So there's, and it's also not quite clear what are the simplest and what are the hardest -1 curves to work with. I just wanted to point this out. This is a good sense of what's involved in the proof of this theorem. Last thing I want to mention is I want to compute something I think is really cool and isn't in a lot of textbooks. So in the 30 seconds I have, I think, I want to just do a computation. So here, the really interesting part of the Picard group is the orthogonal complement to k of x and f. So I want to compute that and pick x bar using the picture. So I want to do it now because I have this picture on the board. And if it's gone, I'll have to write it again. So here's the generators. We have row 1. I'm sorry, this is E1 minus E2. All the way up to E r minus 1. And when I compute the intersection matrix, I get something like this. Does anyone recognize this matrix? Yeah, it's a DR root system. Yeah. So this is a DR root system. So this is a neat fact that helps to explain what the structure of the Galois representations will look like. All right, thank you for your patience.